Hello everyone, in this recording I'm going to be talking about secret key cryptography. Alright, so in secret key cryptography, as we looked before, we use one key, right? So secret key cryptography techniques take a plain text, take a key, use both are input to an algorithm that produces ciphertext. To take back the plain text, we have to pass the key, same key, to an algorithm that works in the reverse order to get us back the plain text. Right? Secret key cryptography has been around for millennia, for decades, centuries, and it is the conventional way to apply cryptography. Right? And it's known by many names: secret key cryptography, or symmetric cryptography, or private key cryptography. All of these, or conventional cryptography, all of these are similar names. Interestingly, now we know why it's secret key cryptography, because we need to keep the key secret. But also we call it symmetric cryptography because both algorithms, the encryption and decryption algorithms, are the same algorithm, just in a reverse order, and both use the same key. Now we will see later that in public key cryptography we don't use the same key, so we will call it asymmetric cryptography. Alright, so the applications of secret key cryptography, we know some of them already, which is data transmission. So we need to keep the information that we transmit, or the message that we transmit to others, secret, so we will encrypt it. And to do that, we have to make sure that both sides, both the sender and receiver, use the same key. So we need to exchange the key, and we need to exchange the key in a secret way. So we don't send the key with the messenger, we don't send the key with the message, we send the key in separate manner. So if you are talking to somebody over a communication channel, you probably wants to send the key in a different way outside of the communication channel, right? Same thing, we can use secret key cryptography to encrypt data that's stored in a storage medium. So I want to keep files or even full hard drives secret, so I'll encrypt those files and store them. In that case, I have to make sure that the key is safe and accessible to me. If it's lost, then it will be hard, if not impossible, to retrieve the data again. Another application of secret key cryptography is authentication. In authentication, we have two parties that they use secret key cryptography to make sure that they each one make sure that the other is whoever says they are, right? So we need to make sure that the identity is correct, right? So in this simple example, we have Alice and Bob. Both are trying to verify that they're talking to each other. They don't see each other face to face, so they want to authenticate each other. And imagine Alice and Bob is a server and a client in a network setting, right? So one way to do the authentication is to both of them agree on a key. Probably they meet over coffee somewhere and they write down a key, each one of them memorize it, so now they know the secret. All right, then over the communication channel, Alice picks a number random number and send it to Bob and ask them, okay, Bob, if you are really Bob, encrypt this random number and send it back to me. So Bob encrypts this number with the key that he has and send it back to Alice. Alice knows the key, right? And knows the random number that she sent. So she decrypts the message from Bob, and if the number that gets back to her is the same as the number that she sends to Bob, well, she knows that's actually Bob because nobody else knows the secret. And it works in reverse order as well. Right, so let me put that in drawings here. So let's say here's Alice, here's Bob. Alice sends a message to Bob saying, here is a random number, Bob. How about you encrypt it and send it back to me? So Bob sends a message back with, this is the encryption of R, the random number, with the key, which results, of course, in encrypted text or ciphertext. Now, Alice knows the R, she sent it already, and she will take ER, decrypt it with her own, with the key that she has. Now, of course, decryption is the reverse of encryption, so eventually she will get R, right? Let's call it R prime here. If R prime is the same as R, then Alice verifies that B is actually Bob. And Bob can do the same thing. He can send another random number of his own. Let's call it S. Alice will send him the encrypted version of it, right? And Bob will verify that by getting S prime, which is the decryption of E S, and both using same key, right? So this is how we do simple authentication. Another application of the secret key cryptography is integrity check. So let's say I'm sending a message and I want to make sure that the message is not changed. Now, we have seen this before in previous courses. We looked at checksum, right? We looked at checksum techniques that are mainly used to make sure that there are no errors in the message. So one of them, we have multiple, but one of them is the CRC, if you remember, cyclic redundancy check. So how we generate the CRC, we apply a formula to the message before we send it. The formula generates the CRC, so we append the CRC and we send it. Now the receiver, if there's any error in the original message, they will generate their own CRC or their own checksum and compare it with this one. If it doesn't match, then there must be an error, right? The checksum sometimes, just in case your maybe CRC is not what you remember, so checksum sometimes in the header itself. So IP header has a checksum where it checks only part of the header, not the whole message, right? And we have the checksum here. That's basically the addition of the content of the header. Okay, so that can also serve as a way to verify that nobody tampered with the message. If somebody intercepted the message, changed few things in it, and send it, now the receiver will find that the CRC don't match or the checksum don't match. The problem with this technique, simple technique, is the interceptor could also change the CRC, could also apply the algorithm and create a new CRC. So this is the original message, let's say the one that was original here. The interceptor, the hacker, can create a new message based on the original one. What they do, they change pieces of the message and then they calculate a new CRC. So the destination will not know that the CRC that it received is different than the original one. It has no way of knowing, right? So this simple technique may be used well for error detection where the error comes from the channel, but it won't be good for some malicious hacker who wants to change the message on purpose, because they can change the CRC as well. So cryptography here can play a role by making sure that the CRC itself does not change. So how do we do that? So we can create a message and we calculate the CRC or something similar. We now forget about the actual CRC that we talk about or we talked about in the Ethernet, for example. But this is just something similar, right? So we can create our own, let's call it checksum, so we eliminate the confusion with the CRC. Right? So let's create checksum here. But the checksum, we just don't put it right away in the message. No, we encrypt it first. So we encrypt it with a key, and the result will append it to the message. Now, anybody who is intercepting this message, if they change something in the message itself, they may still calculate the CS, the checksum, but they don't know how to encrypt the message because they don't have the key. So they will never be able to replicate the same checksum as or similar checksum as the one that was sent originally. So that will be a deterrent for anybody to change the message because they know that, well, they won't be able to create the same checksum, encrypted checksum. The destination, of course, has to know what the key is. So what they do, they take the message here, they calculate the checksum, they decrypt the original checksum here, decrypt it, so they get back the CS, and they compare the two. If the two match, then the message was not tampered with and everything is okay. So these are the four main applications for public secret key cryptography. Now, most modern cryptography algorithms rely on the SP networks. Remember last time when we talked about taking blocks of binary sequence and change it to another binary sequence instead of doing substitution and transposition, right? So modern networks use these SP networks, which are blocks that takes input, n-bit input, and give us another input. Inside these blocks, the bits are shuffled, right? Bits are shuffled in a way that, the input is or substituted with another, right? Whatever input we give is substituted with another. So this is similar to what we talked about earlier when we looked at the binary block substitution. Now imagine these are binary block substitution. But when we talked about this last time, I said that, having or saving a large number of bits here, 32, 64-bit blocks will be, or bitmap will be really impractical because we need a huge memory. So the solution is to actually take any number of bits and break it into smaller number of bits. And instead of having a map of 64 to 64, we will have a map of 4 to 4 or 6 to 6, right? A small map. So small map can be saved in a small table inside our computer, or the algorithm can deal with it. So we can take 64-bit of data block, split it into smaller chunks, and apply this method to each small size block. Okay, so in this case here you can see that we can have a 16-bit block divided into four 4-bit blocks, and we can take every input, pass it through this S box, and generates an output. To add to the confusion, so each one of these outputs from the S box can go to another layer of output. And if we do this in programming, right, we can pass this over and over and over for multiple layers. So we can put a for loop here or something similar, and we can take the output from the first set of, or we take the first set of outputs, pass it again to the same S boxes, but in different variations of input to output, and pass it again, pass it again, pass it again. So this will be rounds. We will call these rounds. And the algorithms that we're going to talk about soon, they are based on this principle, right? So we take output from one iteration, spread it around to multiple outputs. Here we can see that the S box to the left here, one output goes to the first S box, another output goes to the second, third output goes to the third, and so on. But we're not actually limited to this. We can mix and match in any way we want, right? And actually, we could also do something different. We could have the outputs XORed in a way it's actually easier and gives us more flexibility, is to have the outputs. So let's say the input of the second iteration is the XOR of 1, 2, right? And the output here is the XOR of the second and third, and so on. So I can have this situation repeated in a different way. So now that is the S box does the mapping, right? Which is the substitution, while passing it, or this part, does the diffusion. And remember, we want substitution and we need diffusion and confusion. So the diffusion is the substitution plus transposition, right? So we are doing the transposition here. The last thing this paragraph says that the more iterations we have, the more rounds we have, the more the relationship between the input and the output becomes less and less and less um, clear, right? Because we are creating more diffusion here. Now, of course, these S boxes, I should add a personal or note here, is these X boxes, they are carefully designed, right? So it's not just a simple mapping. They are carefully designed so that, the confusion happen in reality rather than just superficially we're doing confusion while at some point probably we're just repeating things over and over. Now, in this course, we're not going to dig deep into the math of cryptography, but actually, cryptography is a well entrenched in math, right? It needs a lot of math background. We just need in this course, our goal is to understand cryptography techniques that are going to use in communication in next courses. All right, the first modern algorithm that we will study is what's called the data encryption standard. The data encryption standard is a technique or scheme that was adopted as a standard cryptography technique by the US in the 1977. It uses key of 56-bit length, right? And it uses also the same concept of the diffusion that we talked about. Now, the DES, because of the 56-bit key, which now is considered too small, it's no longer considered a strong cryptography technique. Or at least by the US, it's not considered a standard cryptography technique anymore. It's still useful. We still use it. You will find it. That's why we're studying it. You will find it in creating VPNs, virtual private networks, and encrypting some wireless communication. So it didn't disappear, but it's not really used anymore to, encrypt highly classified information. All right, so how does the DS work? So first of all, the 50 or the 56 key, the 56-bit key is enlarged to become 64. So how do we do that? Well, the 56-bit key is divided into 7 bits here. Each bit we calculate a binary, not binary, sorry, parity bit. So it becomes 8, and we add a parity bit here, so it becomes 8, and so on. So it becomes 8 and 8 and 8. So now we have 8 by 8. We get 64. Now we still consider the key of 56-bit key rather than 64-bit key. Why we do that? Because actually somebody can generate 56-bit keys and then calculate the 64 by just calculating the binary, the parity bit, right? So we cannot really consider it a true 64-bit key because these bits that we added, they are not random. The other 56 bits are random. But once we know 56, we can generate the 64 by just looking at the parity bit, right? We generate parity bit. So we still consider this algorithm as a 56-bit key algorithm and not 64. Okay. So if we look at this diagram here, we see how or the general structure of the DS algorithm. We have the initial permutation, we have the round 1, 2, 3, 4 up to 16, and we have the final permutation. And then we have the input here is 56 key input, and then we have something called round key generator, which generates key 1, key 2, key up to key 16, and these smaller keys are 48-bit. So let's take one step at a time. Right? So how do we generate the key 1, key 2, key 3? We don't really want to describe this in detail, but let's say we have 64-bit key. All right. So 10100001, something like that, right? So we could simply say K1, the first key is the first two, then skip two, then the second two, then skip two, then the third two, and so on. So we generate 48-bit from this. The second key, it could be based on these two, and then skip one, and then these three, and then skip one. So we generate another 48-bit. So we can generate we can generate 16 keys, sub-keys from the original main key here by just taking subsets. All right, so that's how we generate the sub-keys. How about the first permutation? So the input has to be also 64-bit, by the way, right? So the input has to be 64-bit. And generally speaking, all the algorithms, the size of the message is same as the size of the key. Some of them they change that, but in the DES the message has to be the same size as the key, which implies that if we have a long document, we have to break it to 64-bit or 8 bytes, right? And then we apply the algorithm. Okay, so the first step here is the permutation. The permutation is simply mapping. So take 64 input, shuffle them, and get me 64 outputs. So the first bit may go here, the fifth bit may go here, the second bit may go here, and so on. So we shuffle the input. We get, so here says that the 64-bit input to initial permutation. This permutation is a special case of substitution in which each bit of the output goes or gets its value from exactly one of the bits in the input, right? So we map each input to output in a certain way, and this will be fixed, right? Okay, then after that, we will pass this to round 1. So what happens in round 1? Round 1 has this picture here in details, or actually each round will have the same procedure. So the 64-bit input are split into two, 32-bit to the left and 32-bit to the right. What happened to how we choose that, right? So initially L0 contains all bits are at even positions, and R0 contains bits at odd positions. So when we have the 64-bit input from after the permutation, so this is after the first permutation, we take all the even numbers. So L0 contains all the even number bits. So we'll take so let's say the green. So if we number these positions as position 0, position 1, position 2, 3, and so on. So the even ones, so 0 and 2 and 4 and 5 and 6 will represent L0. and the odd ones, let's do them in red, will be R0 initially, right? So that the first round. So now we have 32-bit to the left, 32-bit to the right. The 32-bit left to the right here goes to something called the Mangler function, which takes one of these keys, the 40-bit keys, as input as well. Then the output of the Mangler function is XORed with the 32-bit that comes from the left, and that will form the 32-bit that will go to the next round, right? You can see here that the 32-bit, each round will have an output. The left 32-bit here, ln plus 1, comes straight from the right input, while the right output comes as an XOR of the left plus whatever comes from the Mangler function. And that repeats and repeats and repeats for 16 rounds. So what is the Mangler function? The Mangler function takes 32-bit and passes this 32-bit into something called or expansion, right? So it expands the 32-bit to become 48-bit. How does it expand? Well, we take the 32-bit, shuffle them, so they're not the same position as the input anymore. We shuffle them, and then we take 16 out of those 32 and duplicate them, right? So if I want to do this in a smaller scale, so let's say here we have 1 0 1 1 as input, not 32 but just small, so we can shuffle them first. So let's say shuffled, so here we shuffle them, and then take half of these and duplicate them. So let's take these half and duplicate them maybe here. So now the 4 become 6, right? Once we finish this step, we can XOR the 48-bit key with the output here. XOR is really one of the most important functions in cryptography, and I mentioned that before. Why? Because when we XOR something with itself, so if I say 1 XOR 1 gives 0, and 1 XOR 0 is 1, and if we say A XOR B is C, but if I XOR that again with B, we get A again. So it's reversible. The XOR operation is reversible. And you can see here that the output, once I XOR it with 1 again, so let's say this is the key and this is the data, right? So key XOR data is this ciphertext. Take the key and XOR it with the ciphertext, we get the data again, right? So that's why we, or cryptographers, like the XOR operation. So we XOR with the key. The key is random, right? Then the output, we pass it to the S box. Remember, the S box does some mapping itself. So here the S box is a little bit modified than the previous. So X box takes 48 and convert them into 32. So how does the X box work? The S box actually multiple divides the 48 block into 6 bits and take each 6 bits and map them to 4, right? So the 48 divided by 6, how many blocks are there, right? So that's 8 6-bit blocks. Each block is mapped into 4. So the result will be 32-bit, and that will be the output. So that's what happens inside each round. We repeat round after round after round. The result of each round will be something that is both included substitution and um, uh, transposition, or as we will call it, diffusion. So we would diffuse, 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 and every time we diffuse, the output will look more and more random, right? And more not related to the input. And then finally, we have the final permutation. The final permutation is the opposite of the original one. So if the original one was like this, it will take us back. So if bit 1 was mapped to bit 3, now the output bit 3 will be mapped back to bit 1. So they are the opposite of each other, right? In general, the algorithm, it works exactly in reverse order for decryption. So if I want to do decryption, it just now the input becomes an output. So the data will go from the bottom. So the final permutation becomes the initial permutation. Round 16 becomes round 1, and so on. So it will the algorithm will be used exactly the same, but in reverse order. Right. Okay. So that is how DS works, without going into the actual mathematical details of how the S boxes are generated or how the subkeys are generated. We won't talk about that, but this is how generally the algorithm work. Now, DS was discovered, or after a while discovered, that it was easy to crack because the technology advanced, right? And now 56-bit key may not be very strong against brute force attacks, for example. So the US actually created the next algorithm, which is the advanced encryption standard. But before that, there was a kind of a immediate solution, or intermediate solution, I should say, where the DS enhanced a little bit, but without changing the algorithm itself. So one of the enhancement was to create the 3DS, which simply means that we take the plain text and pass it through the DS once, then we pass it through the DS again, then we pass it through the algorithm one more time, and then we take, this is our ciphertext. Okay, now if I just want to use one key for all of these, I didn't really enhance the situation, because for brute force attack, if someone discovers the key, well, it's not a problem going and doing the same thing like the decryption, 3 stages of decryption. So just keeping the key the same is not useful. Okay, so we could use 2 keys. So we could use, or 3. So we could use 1 key for encryption here, and we'll call this key K1, and same one for this stage, and this one for the middle stage. So we encrypt with one key, and then we encrypt again with another key, and then we encrypt for third time with the same key as the first one. That effectively, if I look at it from the brute force attack, increases the size from 56 to, so we added another 56, right? So this one is 56 and another one is 56, so we have two of them, all right? If someone wants to attack this, they have to generate um, two of these to be able to figure out what the key is. The other option is to generate three keys. So that means that we don't repeat any of them. So we have K1, K2, K3, and each one of these stages is encrypted with a different key. So why don't we go with the big one anyways? Why do we have these options, either 2 or 3? The problem is the bigger size of the key is, the more difficult for the problem with exchanging it with somebody else, right? And also we have to make sure that these are really random and really unique. So how many ways we can generate 56-bit key at random? So at some point, well, there is what I'm trying to say is there is computational difficulty for generating these random numbers and also exchanging them, right? So we have to have a trade-off. We want something really strong, we have to generate 3 different keys. We have something medium, we use 2 keys. And of course, if we have 1 key, then we better use just a DES, because 3DS doesn't matter. It doesn't really help or doesn't add any difficulty, right? Okay, so these will be called. We will have names, and the names will give us a clue about the technique and the number of keys. So this technique that I mentioned, it can be called EEE, or let's call it 3DAS, EEE2. So encryption, 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 and then with 2 keys, or EEE with 3 keys, right? There is another approach that uses DS, so that's encryption, and then DS but in reverse, so that's decryption, and then encryption again. So wait a minute, what does it mean? We have encryption, then we have decryption, and then encryption again. This means that it cancel each other, right? Well, not really, unless we use the same key. So here is the scenario. Let's say we use key K1 to encrypt, and then we pass the data, this C1 here, to another algorithm that does decryption with K2. So what happens if you pass the algorithm to pass the data to a decryption algorithm, but with a different key? We can't get our original data back. We are simply ruining it more. We are actually encrypting it more. So if we look at this graph, right? So taking the data from the top to the bottom does encryption with a key. But if I pass it backward with the same key, I do decryption. But if I pass it backward from the bottom to the top, but with a different key, I'm actually doing more encryption. So encryption, decryption with a different key will give us more encryption. And then the third one, I can have the third one with the third key. Right? Can I use two keys? Yes, you can use two keys, but as long as they're not applicable to the, if you use K1 here and K1 here, then you are canceling. You're doing encryption and doing decryption again, you're canceling, right? But if you use this example where you have encryption with one key, decryption with another key, and encryption again with the same key, so now you have E, D, E with two keys, or E, D, E with three keys. Right? So the question here, why do I need to do encryption, decryption, encryption? Why don't I just stick to encryption, encryption, encryption? Actually, this one is stronger than E, E, E. Why? Why it's stronger? Now, DS has permutation, and then rounds, and then the reverse permutation. If I stack one DS after another, so you have permutation here with rounds and then permutation here, this one is inverse of this one, so they cancel each other. It's like I didn't do any permutation, any shuffling here. But if I put so let me choose a different color here just to illustrate. Let's say the black is permutation and the red is inverse permutation. So because the red one is inverse of the black one, they cancel each other. So this is encryption, encryption. If I do encryption followed by decryption, so that's the encryption, rounds, and this is the permutation, so the black and red are inverse of each other. And then I do decryption. This is decryption. So the decryption will take the data from the bottom up. So we'll have a permutation here, and then the opposite one will be at the bottom. So these two, they don't cancel each other because they're not inverse of each other, right? So this is why the EDE is considered stronger than the EEE. Right? Now this is a detail that probably you will see or you encounter at some point when we go into the discussion of or some of the tutorial or some of the assignments. Right? But keep that in mind. Now, later, the US decided to abandon DS, or at least it's not the standard technique anymore. And there was a competition, and actually many organizations and people, researchers, proposed schemes, different schemes, and the one that won was Advanced Encryption Standard, or the AES. The AES has same concept, slightly different approach, obviously, but the same concept of rounds. So the first thing that they did was to increase the size of the key. So actually the AES has three different flavors. It can take 128-bit key, or 192-bit key, or 256-bit key. The message itself is always 128-bit, so it takes 128-bit message, but the keys can be exactly as the message length or 192 or 256. All right. Same as DES, we won't get into the details of the math, but we will look at how the rounds work. So here you see there is the same idea of taking the key and generating subkeys. Here actually the difference is there is instead of having a sub key, so we started with 64-bit key and we broke it down to 16 48-bit keys. Here we'll take 128-bit and generates R number of keys. Each one of them is 128-bit. So how can we generate a 128-bit key from already 128-bit key? Well, there is a formula, right? So there is a formula. Let's say, I'm just saying hypothetically, multiply the key by 2 and subtract something so you get the first 128, and then do similar formula and you get the second key and so on. So notice here the R, the number of rounds, is not constant. Why? They actually change depends on the size of the key. So if we have 128-bit key, we use 10 rounds. If we have 192-bit key, we use 12 rounds, and if we use 256-bit key, we use 14 rounds. So the minimum is 10, but we can have 12 or 14. The longer the key is, the more rounds we have. Also, we have here the phases. So we have the initial round, which includes only one operation, which is the add round key. And then we have the main rounds. That's from 1 to 9, right? And we have all of these operations. And then the final round is the same, except it doesn't have the mixed columns thing. Okay, so what happens to the initial round? So what happens for the initial round? So before encryption, the 128-bit plaintext is XORed with the initial key, and the result is arranged as 4 by 4 bytes matrix. Right. So we have K0. It's not shown here, but there is K0, which is the original key, and XORed with, so we have 128-bit message with 128-bit key and message, XOR them together. So the result is the XOR is arranged into a 4 by 4 byte. So sorry, it's 4 by 4, so we need more columns here and more rows. So this is 8-bit, 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 8-bit. So that's 32 multiplied by 4, we get 128. So we arrange them in this matrix. And in fact, all the operations for the AES are based on matrix manipulation, right? So the key expansion, which happens in this box here, takes the initial key and use it to come up with a series of other keys. Now we have a specific schedule or a formula, as I said before, that takes these keys from the original key, right? You can search for them or Google them and see more details if you wish. Now, the operation of the sub-byte, which happens in the main round, so from round 1, 2 up to round nr-1, which is n9, round 9, if we are using only 128 bits. So what happens in these? So we'll take each byte and pass it to S box. The S boxes here are exactly the same. So for the DES, the S boxes are different. We talked about different 6 S boxes. Each one of them represents a different mapping. Here, all the S boxes are the same, right? And this is actually what the S box looks. So if the byte is 1A, so we'll say 1A, and the intersection of the two is A2 here. The A2 will be the output, right? So we can say, well, if the input is 8, 6, so the output will be 44. So that's the mapping. It takes the input as a byte and gives us a byte as an output. And the fact that they are all the same, so we have only one table for all of them. And then we have something called shift rows. So how do we shift the rows? So this is the box, the matrix that we talked about earlier, right? After we substitute, after we pass each byte to S box, we get different byte, right? And then we do something called shifting or shift rows, where the first row doesn't change. The second row shifts by taking the most left byte here and rotate it. So we're doing rotation. So the first one doesn't change. The second one, we take this and move it here, and we shift everything else. For the third row, we shift twice. So this one goes here, this byte goes here, and this byte goes to this one, right? So we shift this way. So we end up with a picture like this one. So actually it's more of a rotation, right? So it rotates everything. That's the shift row. The mix column is the diffusion part. So we did substitution with the S box. The diffusion is we take the matrix and multiply it with another matrix. So the result of the multiplication is actually diffuses the data, right? Just spread it around. And then finally, we do XOR with the key. So the XOR with the key comes at the end. So as we saw here, take the round, substitute the bytes, then shift the rows, then mix the columns, and then we XOR with the key. By the way, adding and XORing are the same thing, right? In Modula 2, add and XOR is the same thing. So you can just simply think of it as XOR with the key. So that repeats. The last round is slightly different. The last round, it doesn't have the mix column. So I didn't draw it here, but just missing the final multiplication here. Now, this is considered by far better than DS. The size of the key at least doubles, if not more. So if we use 128, that's actually double the 64, or even more than double the 56, original 56. Okay, so that these are the two algorithms that used by the US government to actually these are used for general encryption. We're not talking about high classified information. In that case, we don't even know what the algorithms are, right? So these are just the standard encryption. But the US is not the only country that creates algorithms. So other people do algorithms as well and do cryptography. So the International Data Encryption Algorithm, or the IDEA, um, um, also was developed to respond to the insufficient key length for the DS. It uses 64-bit blocks, but the key is 128. So the key is 128 like the AES, but the size of the data block is 64, which means that we take a block, any document, and split it into 64-bit documents or blocks, and then we apply the algorithm to each one of them. Here, generally speaking, we have same idea. We have these rounds, or just we don't get into the details. So we can take the 128 and split it into 52 16-bit subkeys, right? And we do XOR and modular operation. So we don't want to go into the details, but the reason or the goal here is to know the algorithm, the size of the key, the size of the message. So you may be asked about what is the size of the message for the AS? Well, it's 128. What is the size of the key? So we have either 128 or 192 or 256, right? And for the IDEA, the block is 64, but the key is 128. For the DS, the block is 64 and the key is 56 actually, but we expand it with parity bits to 64. Okay, so now we come to the topic of modes of operations. With modes of operation, these are the way we break the data blocks into smaller blocks and we implement them. But we have some challenges doing that, right? So we're gonna take a look at these challenges once in the next part of this recording. So let's start with the simplest approach to take a big block of data, big file, and chop it into smaller blocks, right? And apply encryption to each one of these blocks. So this is what's called electronic code block, right? And the whole idea of taking a big file and breaking it into small pieces and apply cryptography to each piece, we call these modes of operations, right? So the first one is the simplest, the ECB. And in the ECB, the idea is to take a message, break into smaller messages. Each one of them is exactly the size of the data block that the encryption algorithm takes. For example, if we're using DS, we will take a block of 64 bits. If we were using AES, we will be using 128-bit blocks, right? So we take these smaller blocks and apply the encryption algorithm for each one of them separately with the key. Of course, the same key. Take message 1, encrypt it with the key, we get a cipher. Take message 2, encrypted with the key, and get the cipher, and so on and so forth until we're done, right? In the other side, we'll do the reverse. We'll take the cipher text, apply the decryption algorithm to it with the same key, we get the message, and then we attach all the messages together, we get the original big message or big file. All right, so that's the simplest one. Now, the simplest one, however, has problems, has disadvantages. Uh, when we it is possible, right, when we break a file into 64-bit blocks, it is possible that some of the blocks will be identical, right? So the same 4 letters or the 8 letters, so for 64 bits, so this means 8 letters, so 8 characters. 8 characters in the original message will be encrypted and result in the exactly same cipher, right? So that means that we can do some analysis on that, and the eavesdropper can collect these ciphertext and build the library of the ciphertext, even if they don't know what they are, but they can infer some of the information and they can use them, right? And as I mentioned earlier, you could at some point remember that, okay, each message will start with the same prefix or same salutation and ends with the same, for example, signature. So you can get some sense of what's going on there, right? And to make this picture clear, see this image here. So the image is a series of pixels, each one of them represented by bits that represent the colors. So the white color will be always encrypted with the same or results with the same color or the same cipher. So the white here at the Dalhousie logo is resulting in these combinations of colors you see here at the edge here at the corner, and the gold color results in the same combinations of pixels here, bits or pixels. So even though you don't see um, the Dalhousie logo in its original form, but you can figure out the picture here. Even though it's encrypted, you can still see the D, you can still see the A. Why? Because we are encrypting the same color and the result with the same key, so the result will be the same cipher. And that applies even to texts, but images or sounds will be even clearer. So the first electronic code book is not the best, even though it's the simplest. We could still use it for something simple like exchanging small bits of information, like a PIN number, right, in the cache machine, or a small password, where the chances of having a big block of data is small, right? Um, Now the next one is better, and it's called the cipher block chaining. With the cipher block chaining, we take the message, and before we encrypt it, we XOR it with a vector, initial vector, any random vector, any random bit, sequence of bits. It has to be the same length. So if the message is 64-bit, the initial vector has to be 64-bit as well. So we XOR them together. The result will be passed through the encryption with the key, and we get the cipher. The cipher can be used to XOR the next message, and we get the result. We encrypt it, we get SC2, we use it to XOR with the third message, and so on, right? So the result of that, because of the XOR, the message that gets into the encryption is never the same, even if the message is the same. If M1 and M2 are the same, but M1 is XORed with the IV here, but M2 is XORed with the C1. So even if the message 1 and message 2 are identical characters, what's encrypted is not the same, and consequently the C1 and C2 and C3 will not be the same. Right? With the 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 reverse, the decryption happened by taking C1, pass it through decryption algorithm, the output will be XORed with the IV. Remember, I said earlier that anything is, if I XOR something with key and then the result XOR it again with the key, I will get the original message. So we will get M1 here. And we'll use the C1 to XOR with the second message and so on, right? So we reverse the process. The output is, in this case, if I use this technique, the output will be at the bottom picture here, bottom block. You see this is the same logo was encrypted with the same algorithm. So the same encryption algorithm, but the top one will use the first technique, electronic code book, and the second one we use the CBC, the cipher block chaining. So the second one we cannot really relate, we cannot even know if this is an image or not. For as far as we know, just a random bits, right? Which means that the CBC is far more superior mode of operation. Okay, so that's the advantage, but the disadvantage is, first of all, this IV thing, it looks like another key, right? It's another key that I need to exchange with the destination, with the recipient. Otherwise, they won't be able to decipher the message. So we need IV here in the encryption, and we need one at the decryption. So we need to send, or we need to exchange effectively two keys. The key for the encryption, decryption, and the initial vector. So we can omit, we can say, okay, instead of exchanging two numbers, how about the IV is always 0? That doesn't change much. The algorithm will still work. You XOR M1 with the IV, you get the same M1, right? So initially you will get the same M1. So anything you XOR with 0, it ends up with the same thing. So A XOR 0 is A. So we get M1, we encrypt it, then we get C1. C1 now is encrypted thing. So we start on always with 0, but the rest will be as usual, continue as usual. So that could be a solution for or to avoid exchanging two numbers. But there is remaining this possibility that someone will be able to figure out um, the cipher if we always start with the same message, with the same set of characters, right? Without XORing it with anything, with XOR it with 0. So someone can collect C1 and M1 for a large number of messages exchanged, and they will be able to do analysis and figure out the relationship between them, right? So you have a risk of having this first block being discovered. Another disadvantage of this technique is that everything is daisy chained. So let's say I am sending the C1 over the channel, and the C1 gets corrupted due to noise, right? So the C1, the part of the message, gets corrupted and we never receive it correctly. So now, if C1 is corrupted, I cannot decipher the rest of the messages because every block depends on the block before it. So if C1 is damaged, I cannot fix the rest. I cannot discover the rest. So that's the major problem with this technique, even though it's quite good in hiding the relationship between the plain text and the ciphertext. The third technique is called the output feedback. The output feedback avoids the problem by saying, it is almost like the one-time pad that we discussed in previous scenario, in previous case. We talked about one-time pad as one of those strongest techniques for encryption. So this technique generates something similar to one-time pad by taking IV, initial vector, which could be anything, right? And encrypt it. So we don't encrypt the message itself. We encrypt the initial vector. We encrypt it. Notice here that I'm looking at the top part of the diagram before the block M blocks. So E, or the output of the encryption, it's passed again to the encryption, and we encrypt the output again, and then we encrypt it again, and we encrypt it again. So what we get out of this is the P0, P1, P2, P3. Imagine the P0 is the output of the first encryption, P1 is the output of the second encryption, and we concatenate them together, so we create a long message that is equal to the size of the message that we want to encrypt. And then we XOR M1 with P0 or P1, depends on what's the index that you start from. M2, you encrypt it with the second block, and M3 you encrypt it with, or you XOR it, I should say, XOR it, and so on. So the output will be the ciphertext will be the output of the XOR function. All right. Is that good encryption? Yes, because now what we get out of the encryption technique, the algorithm, is something that is the result of encrypting the initial vector. So we don't know what it is, right? When we XOR it with the M1, we get something that's like something encrypted XORed with the message. So what we get is something almost look like random, the result of the encryption there, right? The advantage of this technique is that we need to calculate the top part, the pad, the one-time pad. We need to calculate it only once. So we can do this once and save it, right? We can generate a long one-time pad, save it, and then every message that comes and we want to encrypt it, we just need to XOR it with the one-time pad. That saves a lot of time, since encryption is a CPU intensive process, right? And sometimes they do it even with special hardware. So if we can manage to do that once and save the one-time pad, and then every encryption would be just performed by the XOR operation, and that's great, right? So that saves us a lot of time. So that's the advantage. Disadvantage, however, is if somebody discovers or somebody gets their hand on the plain text and the ciphertext, the two can be XORed, and we get the one-time pad. That's the problem, right? So let me illustrate that. Let's start by, let's put this on the side, maybe, or just go and look at the board here. So we have the IV, initial vector. We pass it through the encryption algorithm, and this is the key, and we get something that we pass it again to another block. All right, so let's use only 2 blocks for now. Right. The output, as I said, we XOR it with the message. We get the cipher. So let's assume that B1 here is the output that we get. So C1 is B1 XOR M1, and C2 will be B2 here. That's M2, and that's C2. Okay, now all of this is great, but if somebody gets their hand on, let's say they get the ciphertext and they get the message, they get their hands on two, so they can simply say, okay, C1 XOR M1, so they can XOR the ciphertext with the message, the plain text. This is equivalent to taking the right side and also XORing it with the message. Now anything XORed with itself gets 0, right? So 1 XOR 1 is 0, and 0 XOR 1, 0 XOR 0 is 0. So these two cancel each other. So the result will be B1. So if somebody managed to get their hands on the message and on the cipher, they can simply XOR them together and get the one-time pad. Is that possible? Yeah, it depends on the protocol we use. It depends on the technique we use. Obviously, if we use this technique, we should use a protocol or an algorithm or a communication protocol that prevents the message from being online at all, right? But if we're not careful, let's say in the example where the two Alice and Bob send their plain text and then for authentication, and the other one sends the encrypted version of that random number, right? We talked about earlier. So in that case, anybody who's listening can get their hands on the two. So if I want to use this authentication technique, I shouldn't be using the one-time pad, right? I shouldn't be using this technique at all. I should avoid using it. For other applications, that's fine, but you have to be careful about which one you use. So for the output feedback here, we have to be careful about its applications. All right, the fourth one will be the cipher feedback, or CFB. CFB tries to do whatever the previous one does, but enhances it a little bit. So it takes initial vector, encrypt the initial vector, same as before, XOR it with the message, get the C1, the cipher. But here you notice that we get the output of the XOR and we use it to encrypt again, right? So we still need the message to generate these keys or these these vectors, I would say, that we need to XOR. So for here, we didn't need the messages at all to generate the one-time pad. But by taking the output after the XOR, we get this system here. Okay, so advantages. Well, we got rid of the problem where we can XOR the M1 and C1 and we get the pad. We don't have this problem anymore, right? But we still have the issue of the chaining. If I lose 1 byte, I may get some of the messages lost. Not all of them, like the first, the CBC, but if 1 byte is lost in transmission, the next 8 bytes will be grabbled, right? But decryption will work properly after that. So we have some limitations. The counter mode, or CTR, is similar to the OFB, similar to the feedback, this one. It takes the initial vector, encrypted, XOR the output with the message, we get the cipher. But here, the initial vector, the next one, it's derived from the first one. So there is no daisy chaining, there is no output feed to the input of the second part. Each one of these blocks are separate. The initial vector, I just need to know the first one, and then the second one. Here it shows that they are increment of 1. So if I know the first one, I can increment the second one by 1, the third one by 2, and so on. And also, if I lose one block here, I'm not losing any more data because I can figure out what is the initial vector for the remaining blocks. Now that doesn't have to be incremented. Like it could be any formula. I think it just the textbook says increment by 1, but it could be any formula. It could be increment by 5, right? Or any relationship between the initial vector and the others. So here, this is good for random access files. Why? Well, imagine I have the situation where I am sending, I have a long file or series of files, and I don't really want to read everything from the beginning, right? I don't. In all the previous techniques, I'm assuming that I'm sending a file and I have to encrypt it from the beginning to the end, and when I decrypt it from the beginning to the end, right? But if I am storing files in a hard drive, sometimes I just want to read the third one or read the fifth one. If I daisy chain the decryption techniques, I have to read all of them from the beginning to get to decrypt the third one. But if I know this is, I'm using the initial vector for the first one, for the second one it's IV plus 1, for the third one is IV plus 2, and so on, I can simply say for the third file I'm just going to use IV plus 2, right? Now we're talking not about files, but we're talking about specific blocks of data, 64-bit or 128-bit. It depends on the encryption technique, but the same concept applies, right? So I don't really need to go from the beginning to decrypt everything. So this is the advantage of this technique. Disadvantage will be same as the OFP, where we have if somebody figure out if we take M1 and C1 and XOR them, we will find out uh, the input or the output of the encryption, right? This part. Okay, all of these techniques are used for encryption, and we call them mode of operation or modes of operation. Then we have one last technique that we use for message authentication. If you remember when I started this recording, I said that one of the applications for secret key cryptography is to make sure that uh, the message is not tampered with, is not being tampered with. So we may not need to encrypt the message itself, but we can take the checksum of the message, encrypt the checksum, send the checksum with the message. So now anybody who tries to tamper with the message, they will not be able to change the checksum, the encrypted one. So here is the message, right? And I pass it through algorithm that generates the checksum, and then the checksum itself is encrypted. So here is the encrypted version of the checksum, and I send it with the message. If somebody changes this without authorization, the checksum that the destination will calculate, it will not match. The destination can calculate the checksum, encrypt it with the key, and compare, or does the reverse, let's say, calculates the checksum, and since they know the key, they can decrypt the encrypted checksum. So now these two have to match. If they don't match, this means that somebody changed the message. The message itself could be plain text. It could be not encrypted, right? Just open. So that's how we make sure that nobody touches the message. And if they touch it, well, then they won't be able to generate the checksum. So we will find out. Okay, so how do we generate this checksum? We could use one of the earlier technique, which is the CPC residue, to generate the checksum. So we know from the CPC residue that we can take the message, XOR it with initial vector, and the result we encrypt it, and we'll do the same thing over and over and over. Right? So this is the same as the CPC technique, except that we actually will throw all these C's, all these ciphers, we'll throw them out. We don't need them. We will keep the last one. This will be our the we'll call it the CPS residue, right? Or the CPC residue actually. So that's our checksum that we sent. So we have several techniques. The CPC residue is the simplest one of them, right? And we have CPC with weak encryption, CPC encryption with CPC residue, and some of these. What's the difference? Why we need to look at all of these? The problem is encryption is expensive in terms of time. So we're doing this over and over and over for every message that goes through a router or a firewall or through a tunnel. It's not something that we want to do without a reason, right? So if I have to do it just so that we can get the CPC residue, I may need to use either encryption technique that's weak. So if we have we talked about several encryption techniques, we will take the DES for example. It's a simple, considered now weak, but it is still good just to do integrity check. May not be good for encryption, but it may be good for just doing the integrity check. So we'll use that technique. Also, even within any encryption algorithm, there are some strong keys and some weak keys. Even let's say, even if I choose 128-bit key, all right, that will be strong key, right? But some people may trade, let's say 10101010, it's considered a weak key. Why? Because people can try it 101010, right? Any key with a specific pattern can is considered weak. Let's say 11111111, right? That's a weak key. Let's say 111000111000, right? All of these are weak keys because we can generate them. They follow a certain pattern, and as I said, at some point we need the keys to be they look like random. Nobody can guess them. So we can, but these maybe we can use them for good, or we put them to good use. We don't throw them. We don't discard them altogether. We could use them for some simple purposes like this. So we could use the CPC with the weak key to generate some of these. Right? We could also um, so if I want to do encryption and integrity check, I can do the encryption with a strong key, and I can do the integrity check with a weak key. Choose one of the considered weak keys and use them for that. Um, I could also use um, um, if I have to do encryption and integrity check at the same time, I could have a key that do the encryption and the key that does the checksum. I'll use it related. I'll use something related to the original key, right? So instead of let's say the original key shifted by 8 bits, so that's related, right? So all of this is intended to avoid using or sending two different keys, right? Because that takes time and we need to exchange more information. Also, avoid using expensive um, or wasting use good keys for something simple like integrity check, right? Um, and do the things faster. So you can see here this part explains the integrity checksum, and this part talks about um, the cases where we need to do privacy and integrity. So we can do the CPC with weak cryptographic checksum, where we actually use two keys. We cannot use one key, right, for both encryption and residue. Why? Because if somebody figure once, well, they will figure the other, right? So we have to use two, but we can use the second one slightly less uh, less good, if I can put it this way. Okay, so all of these techniques, I think I covered everything here. They can be mathematically related to each other. Um, we could also do something like hash the message and then encrypt it. So this is something that we will look at later when we'll talk about hashing. So we'll keep that in mind. Um, so yeah, that's cover everything, and that will um, conclude this chapter. And I will hopefully see you in the next recording. So thank you for listening, and we'll see you next.